when we use the fundamental theorem of algebra, all we have to do is identify the degree of the polynomial, and then we're going to be able to tell you how many total zeros there are. So in that first example, what's the degree of that polynomial? 4. It may not be the first term, but it is the highest exponent, which means how many zeros are we going to find total? 4. Some of them might be real, some of them might be repeated, some of them might be imaginary. In the second example, fundamental theorem of algebra tells me that this polynomial will have how many? 5, because it's degree 5. Makes sense. I feel it's like one of those things, like I feel like I already knew that. You probably did. But we can use the fundamental theorem of algebra to very quickly determine what type of zeros I'm going to find for different polynomials. So let's say we have these graphs, and we want to use the equations and graphs to identify the total number of zeros in each equation according to the fundamental theorem of algebra. Remember, that's the degree of the polynomial. And determine how many real and how many non-real. So real solutions are going to show up on the graph. These are the ones that we can see actually crossing the x-axis. They may be fractions, they may be whole numbers, but we can see them on the graph. Non-real solutions are basically what's left. That's not how you spell the word what. I almost just spelled it wrong. What's left? Your leftovers or your other. Okay, real solutions can be seen on a graph. Non-real solutions or imaginary solutions cannot. So if you look at that first example, f of x equal to x to the 4th minus 2x squared minus 7x plus 6. What is the degree of this polynomial? 4. So there should be 4 total zeros. We know that from the fundamental theorem of algebra. But based on the graph, how many real zeros do I see? 2, which means how many of them are going to be imaginary? There you go. We know now when we would do the P's and Q's thing, we would know we were looking for 2 real zeros, and the 2 of them are going to be imaginary or complex numbers. So for the second one, how many total zeros? 3 total zeros, because that's the degree of the polynomial, but how many are going to be real? Only 1 is crossing the x-axis, so only 1 is going to be real. The other 2 must be imaginary. Now, it's no coincidence that there are both even numbers for imaginary zeros. There will always be an even number of imaginary zeros, if any, because we have this other theorem or idea called complex conjugate zero. It says that if a is equal to a plus bi, and that is a zero of the polynomial, then automatically we know that x equals to a minus bi is also a zero. That's called the complex conjugate. If you think back to the P chapter that we did at the very beginning of this class, we dealt with the complex conjugates. We did a whole lot with them, but that is the complex conjugate. Every single time that there is an imaginary answer, there's actually 2 because you have the plus version and the minus version of the imaginary part. Okay, so we're told on example 2, one of the solutions to the equation x squared minus 4x plus 5 equals 0 is this imaginary number 2 plus I. Okay, we're given this piece of information. We're going to use synthetic division to verify that it is a solution. To verify that it's a solution, we just need to make sure that the remainder is what? That the remainder is 0 when we use synthetic division. That would verify that it is a 0. Okay? So we set up synthetic division. I'm going to have 2 and positive I as the number I'm dividing by. Don't panic. We have the numbers 1, negative 4, and 5 as my coefficients. The steps to synthetically divide are bring down, multiply. Now, I'm multiplying 2i times 1. What is 2i times 1? 2i. 2 plus I. Like literally, it's the same thing, right? Anything times 1 is that anything. It's a complex number. When you're adding complex numbers to real numbers, all you have to do is add the real parts. What's negative 4 plus 2? Negative 2, and then the I didn't add with anything like that. It's adding like terms. There was no imaginary part to that one, but there was a real part. And then, yikes, guess what we need to multiply next? Negative 2i times 2i. Sorry, I keep saying that wrong. Negative 2 plus I times 2 plus I. And I'm sure you're thinking, oh, I really don't want to do the FOIL method and have to remember what I squared is. Great, look at your calculator for a hot second. Above the period button, what do you see is there? Oh my gosh, your calculator can do arithmetic with imaginary numbers. So right now in your calculator, I want you to type parentheses 2 plus I times parentheses negative 2 plus I. What do we get when we type that in? Negative 5. If we had done this by hand, which if you ever look at the online version of these notes, I did it by hand on there just to show you and prove it to you that it works. We would get negative 5. And 5 plus negative 5 is 0. Is 0. We have verified that that actually is a solution. This question goes on to ask, what is the other solution? Well, if we think about the fact that synthetic division is now telling me the factor I have left is x minus negative 2 plus I, right? Because this is the remainder, this is the constant, this is the x term. We've always taken the other 0 to be the c value. So the other 0 is negative 2 plus I, which is exactly what I got as my constant left over. So we learned a couple things from this example. Number one, complex conjugate zeros are always there. We also learned that you can do synthetic division with imaginary numbers. You can do all types of arithmetic with imaginary numbers. You can add them, subtract them, multiply them, divide them. Bless you. Okay, so now we're not stopping whenever we would get to an imaginary solution. We're going to keep going. But to refresh memory on what imaginary solutions are, I've done some work for you here. Factors of a polynomial with real coefficients. So every polynomial with real coefficients, aka like numbers like 5, 2, negative 3, negative 5 as coefficients, can be written as a product of what are called linear factors. This is something we're used to. You didn't know they were called linear factors, but they are. That's x minus c. And something called irreducible. And I always spell this word wrong, so give me a second. See, I still spelled it wrong. Hold on. It's one of those words, you know those words you just can't spell correctly no matter how much you try? Irreducible and necessarily are the words I cannot spell correct. Necessarily, I can never spell that word right. And I still put a y at the end. Irreducible. Wednesday, Wednesday. I have to say it like that though. Wednesday. Restaurant, also very hard. Autocorrect always fixes the word restaurant. Huh? Not out loud. Hold on. F-E-B-R. No, hold on. R-U-A-R-Y. February? No. February. I'm stressed. I also got out of the spelling bee in elementary school on the word rumble in the 3rd grade. Rumble, guys. Rumble. Spelling is not my forte, especially out loud. I can look at stuff and be like, that's spelled wrong, but I don't know how to fix it. I just cannot out loud. Spelling is not my. Anyways, okay, so an irreducible quadratic factor is a quadratic with no real solutions, aka two complex or two imaginary zeros. So a polynomial here, we have an example. This polynomial x cubed minus x squared minus x minus 10 can be factored to be written as x plus 2, which is a normal linear factor, times x squared minus 3x plus 5, where, like I just said, x plus 2 is the linear factor. That's something we're used to seeing. That's what we did last time. They were linear or real factors. And this other piece, x squared minus 3x plus 5, is an irreducible quadratic factor. I wouldn't be able to factor that without making it an imaginary number. So my answers are going to have i's in them today. Okay, so we look at the example I've done for you. There's a lot of algebra in here, so we're going to look at it piece by piece. Suppose you have a polynomial with the zeros x equal to negative 2 and x equal to 3 plus I. The first question is, what is the minimum degree of this polynomial? Assuming none of them repeat, I have 3 zeros. I know this because not only am I given 2 of them, this is a complex number, which means its conjugate is also a 0. So I have 3 potential zeros here. These have to come in pairs. So this is for sure at least going to be degree 3. Maybe there's some multiplicities there. We don't really care. We're going for the smallest amount of work possible. The part B says to write the polynomial in factored form with the given zeros and use linear factors, aka x minus some number. So here's my linear factor, x plus 2. That one's always going to stay linear. And we've written the irreducible quadratic factors out as linear factors. Look, I took x minus the 0, 3 plus I, and x minus the 0, 3 minus I. See how I plugged them in like I would have plugged in like a regular number if that were not a complex number? Fabulous. That's factored form with linear factors, but we want to eventually write it as a product of linear and irreducible quadratic factors with real coefficients, so we have to do the following work. Let's just figure out what I did so we can write down what I did in each step. The first step here is exactly the problem before it. I just rewrote it because I needed it to be closer for myself. What did I do to get from this line to this line? Can anybody figure it out? This polynomial has been FOILed. You are correct. What I did was I took x times x, that's x squared. I took x times the second part, which is negative 3 minus I, and I did negative x times 3 minus I. And then I FOILed this one, negative 3 plus I times x, that's negative x, 3 plus I. And then the last two parts, negative 3 plus I times negative 3 minus I is positive 3 plus I, 3 minus I. I FOILed it. Here we go. Okay. We did x times x, x squared. Do we follow that one? Okay, fab. Then we take x times this whole thing, which is just x times this whole thing. Okay, then I took this and I multiplied it times x, which is x times the whole thing. And then I did the whole thing times the whole thing. And for right now, I just put them next to each other, indicating that I multiplied them. Because that's a lot of math to do in one step. We just FOILed it. If you want to write a note for yourself, that's what I did. I FOILed it. First, outer, inner, last. Okay. Can anybody... Oh, yes, question? Okay. What did I do to go from the second line to the third? I distributed here. Okay, so negative x times 3 is negative 3x. Negative x times negative I is positive xi. Negative x times 3 is negative 3x. Negative x times I is negative xi. Okay. Where did this come from?
You FOILed.
I FOILed this one. 3 times 3 is 9. 3 times negative I is negative 3i. I times 3 is 3i. I times negative I is negative I squared.
Well, that's negative 1.
Ah, that's negative 1. Great. So we did that here.
Isn't it possible?
It will eventually be positive 1 because we're subtracting it, yes. But what did I do to go from here to here besides I squared equal to negative 1? There's a whole bunch I can cancel out. I have positive xi and negative xi. I have positive 3i and negative 3i. And if I condense all of that down, I have like terms of negative 3x and negative 3x. Those will add together to make negative 6x. And then I have that 9. And then the negative I squared, which is like doing I minus negative 1. 9 minus negative 1. Which is like 9 plus 1. And voila, I have arrived at my linear factor and my irreducible quadratic factor. It's a lot of foiling. Take your time. How much does the foil cost? $10. 20 Quigley bucks. The very last part of this question asks you to write your polynomial in standard form. Not with the factors showing, but in standard form, which means all multiplied out. So to go from here to here, I just double distributed.
Does that mean you FOILed that?
It's not technically following the FOIL letters, but yes, I would double distribute x times x squared, x times negative 6, x times 10. That's right here. And then 2 times x squared, 2 times negative 12, and 2 times 10. That's right here. How'd I go from here to here? I combined my like terms. I've got a couple squared terms, so I'm going to add those together. And then I have a couple x terms, which I'm going to add together to arrive at my final polynomial. Oh my goodness. That's a lot of math.
Wait, is there a question?
Yes.
Did you get negative 6x squared plus 2x squared? And how did you get to just x squared?
I'm here. You got this one, right? You know how I got this?
Yes.
Do we know how I got this one?
Yes.
Okay. Negative 6x squared plus 2x is like negative 6 plus 2, which is negative 4.
Oh, I was looking at the wrong one. Because you wrote x squared.
Oh, it's just funky looking. Is that what you're looking at? Where did I mess up?
The final one where it says x squared.
Oh,
Yeah, that's what was the negative.
that should be a cubed. My bad. Thank you. Look at all my mistakes I'm making today. My human is showing so much.
It's Wednesday.
It's Wednesday.
Wednesday, guys.
Now, the next type of question that we can be asked about is to find all the zeros of a polynomial function. Last time, you would have stopped right here after this step because we didn't know about the complex stuff. It's not that many more steps, just a little bit more work to do. So for number A, they gave us this polynomial and they gave us 2 zeros to start with. They gave us that x is equal to negative 1 and 2/5. So we don't have to do the p's and q's stuff because they gave me numbers to start with. Those are the numbers I'm going to synthetically divide by, which you can see here. You'd synthetically divide. Don't panic that it's a fraction. You can still multiply numbers by fractions and synthetically divide by it. Both of them should come out to 0 because we're told that they are zeros. Amazing. I'm left with, at the end of my synthetic division, this polynomial, which, if you remember, this is your remainder, this is your constant, this is your x, this is your x squared term. This is the polynomial 5x squared plus 5. That's what I'm left with at the end. But we want to know what the zeros are for that part of the graph as well. So what we do is we take the leftover polynomial, we set it equal to 0, and we solve. Subtract 5 to both sides, divide by 5, square root. Square root of negative 1 is I, plus or minus I. So once we get this, we know all of the rest of the zeros. We know this degree 4 polynomial had 2 real solutions, because they were given to us, and 2 imaginary solutions, and so they're listed here on the side of your paper. The zeros are negative 1, 2/5, and plus or minus I.
Like square root of negative 1 is
Mm-hmm.
That was given to us, right? I mean,
Yes.
the other two was given to us.
The other 2 were given to us, yes. Okay, so you're going to kind of do the same thing in part B. We'd follow the same sort of steps here, but this time, what 0 did they give you?
2 plus I.
Which means they also gave you what? 2 minus I. So really, when they give you one of the complex ones, they've given you both of the complex ones, which is kind of nice because now I don't have to do any of the p's and q's stuff to try to find it. Okay, but we're just going to start doing some synthetic division with complex numbers. Don't forget your calculator has a function for this, so you can do a lot of the arithmetic in the calculator. Okay, so we fill out all the coefficients. This is 1, -4, 36, and -45. Bonus question right now. Based on the fundamental theorem of algebra, how many total zeros should I find? 4. Okay, fabulous. So we know we have 2 of them. Means we're looking for 2 of them. What's up? No, it's not worth a clue.
This is a bonus question.
So we bring down, we multiply, we add. We would multiply, which again can be done in your calculator. Has anybody done that yet? -5, good. We add. We would multiply, which is just -9 times 2 and -9 times I. Just distribute the -9. We would add, which is 18 minus 9i. Again, just adding the real parts. And we multiply, which thank goodness is 45. We knew it would work. We knew we would get a remainder of 0 because we were told it was a factor or that it was a 0. What's the next thing I synthetically divide by? Or 2 minus I. Yeah, you change the real or the imaginary part. So we bring down, we multiply, we add. Check out what's going to happen when we add negative 2 plus I and 2 minus I. What do you get? 0. Then you multiply, it's still 0. You add, that's negative 9. You multiply 2 times negative 9, negative 18. 2 times minus I plus 9I. We add. Again, the arithmetic with imaginary numbers can be done with the aid of a calculator. Don't let that be the reason that you mess up. Now we just need to figure out how to solve what's left. What is left, by the way? We've got our remainder. X squared minus 9. Fabulous. Well, x squared minus 9 is what we're going to be solving on the side here, because that's the part of this function that we don't know the solutions for yet. What do I do to solve for x? Subtract it? Add it. Okay, and then I take the square root of both sides. What's the square root of 9? So plus or minus 3 are the other zeros. So if we were to graph this polynomial, we would see it crossing the x-axis at 3 and at negative 3. That was finishing finding all of the zeros, which means that all of my zeros altogether are the numbers x equal to 2 plus or minus I and plus or minus 3. But potentially the question could not give you any zeros to start with, in which case we'd go back to what we learned last time with the P's and the Q's. So if we look at the first example here, it's kind of gnarly. We weren't given anything to start with, so we don't know what number to start dividing by. When you don't know what number to start dividing by, you go to the list of potential rational zeros. For this one, the P was 20 and the Q was 3. Here's all the numbers that multiply to 20 and the numbers that multiply to 3, which means the combo list would be plus or minus 1, 2, 4, 5, 10, 20, and then 1/3, 2/3, 4/3, 5/3, 10/3, and 20/3. Yuck. You'd go to your calculator, you'd check out of all of those terms, all 14 of them, no, 28 of them, which one of them you could use, and your calculator would return to you that negative 4 and 1/3 work. Therefore, how many imaginary solutions would I have? 2. Since this is a degree 4 polynomial, we know there has to be 4 zeros. Only 2 of them are real, because the real ones have to be in that list, so 2 of them are imaginary. Great, so we're going to take those 2 zeros that we found, and we're going to do synthetic division. We see that. And we arrive at the linear factors, which are the real ones, and the irreducible quadratic factor, which is what's left over in the bottom. But since this question still wants us to find all of the zeros, we need to take that irreducible quadratic factor and solve it. The only way to do that is either by completing the square or the quadratic formula. Remember, the quadratic formula is x equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. We'd start reducing. This is 144 minus 12 times 15, which I don't feel like doing in my head, gives you negative 36. The square root of negative 36 is 6i. 12 divided by 6 and 6 divided by 6 both go. So this is going to be 2 plus or minus I. So all of my zeros, the 2 that I found that are real from the P's and Q's, negative 4 and 1/3, and the zeros that I found that were not real, 2 plus or minus I. That's the big kahuna. That's the big kahuna type of problem that I could ask you to do for these notes for this lesson. We're finding all of the zeros for any polynomial possible.
So you're using quadratic function, right?
You probably would use the quadratic formula, yes. Now there's a chance if it's just like x squared plus 1, like you can solve that just by square rooting both sides. But for the most part, you're going to be needing that quadratic formula. Let's do one together. We probably won't do both of these examples because they're very similar. They're both online though if you want to look at them. We'll do number B. Okay, if we're trying to factor this, we don't have anywhere to start. We start with P's and Q's. P is 15. What is Q? 1. By the way, how many zeros am I trying to find for this graph? 3. Okay, cool. Let's make a list of all the potential rational zeros first. So P is equal to 15. The things that multiply to 15 are 1, 3, 5, and 15. The things that multiply to Q are just 1. Phew, 1 times 1. The list of potential rational zeros is the combo of all of these numbers. Plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. There's only 8 options here. That's so much nicer than the entire number line. What do we do to find the real zeros? Yes, you should be reaching for your calculator. Go ahead and find me, out of this list, which one of them are real zeros. You have to test all of them, but you know we're looking for at most 3. Were there any other numbers besides -3 that work? No, which means how many of my solutions are imaginary? 2 of them are imaginary. And remember, they always have to come in pairs. So if you ended up with just one imaginary, something went wrong. Imaginary numbers come in pairs. So we know there's going to be 2 imaginary. Let's go ahead and just divide this one out to get rid of it. We would divide this polynomial by -3. This is, why did I start with x? This would be 1, 1, -1, 15. Bring down, multiply, add, multiply, add, multiply, add. We know it should equal 0 at the end for the remainder because it is for sure a factor. We got it off of our list. Which means I can factor this to the linear factor of x plus 3 and the irreducible quadratic factor of the leftovers, x squared minus 2x plus 5. That's where we would have stopped last class, but now we're remembering about quadratic equations having imaginary solutions or imaginary roots, so we can go do the quadratic formula for that blue equation. This would be x squared minus 2x plus 5 equal to 0. And if we're solving this using the quadratic formula, it's x equal to -b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Do we know where all the numbers came from? We just maybe need to memorize the quadratic formula, right? Okay, put that on your to-do list. We can learn it in song if you want.
What was it again?
It goes to pop goes the weasel. Do y'all know that one?
No, it was
It's
something.
about like
Miss
4
Grace.
awesome chicks.
That was Miss
Oh.
Grace.
I never remember that story. I just learned it in song.
So what was the number?
It's to the tune of Pop Goes the Weasel, okay? Do you know Pop Goes the Weasel?
No.
Y'all don't know Pop Goes the Weasel?
I don't know.
The Pop Goes the Weasel song. No? Okay. Well, it goes x equals -b plus or minus the square root of b squared minus 4ac all over 2a. Thank you. Thank you. Appreciate it. When my singing career ends. So we would reduce this. Yes, I know you have calculators, but if we do this a little bit by hand, this is 2 plus or minus the square root of 4 minus 20, which is -16, over 2. What's the square root of -16? 4i. So this is going to be 2 plus or minus 4i all over 2. Since both the first part and the second part are divisible by 2, we can reduce that. This is going to be 1 plus or minus 2i. here are the imaginary roots or solutions to this polynomial. So if we wrote down all of the zeros together, we would have the 2 that they gave us, or so two, sorry, the 1 we got out of the PRZ list, and then the 2 that we got out of the quadratic formula. That's the process you're going to be doing over and over again for these problems. Starting from P's and Q's, getting to the factored version, and then finding all of the zeros. It's
I feel like 2i equals I wanna cry.
2i equals I want to cry. Nah, it would be great.